Hi. So this is the fourth video, and in this video we'll focus about specific architectures. In previous videos, we learned about different components, individual components of the multi-head attention and the masked attention. And in this video, we'll try to kind of combine the components into specific pipelines, infrastructure, architectures of transformer, and we'll give a couple of examples. Now, the first is for text. Okay, so let's consider here the input consists of sentences or paragraphs, and we have a short sentence. The sentence, as we already discussed, is broken up into tokens. Okay, so as we said here in this video, tokens a word. In general, it's not necessarily so. And we have an embedding vocabulary. Okay, so each token obtains or is computed a certain vector embedding. And this vocabulary is a trainable part of this network in modern architectures. Okay, so here we have, for example, for words, you keep using, and word, each one of these tokens has a different embedding. And these words are the input to kind of like the heart of the transformer, which is the mask multi-head attention. Okay, so we have the mask multi-head attention. Again, we have a one-dimensional kind of sequence of words, and the whole idea is to train the network to predict the next word. So in general, what we want to do is we want kind of previous word to affect future words, but not vice versa. So when we use the mask multi-head attention, we kind of block certain edges in the attention graph. Okay, so we make sure that future words do not affect kind of previous words. Okay, so this is the mask multi-head attention, and it's repeated usually several times. So we have several such masks, and you can think about it that, for example, the first attention or multi-head attention takes into account kind of all pairwise interactions and then applies a nonlinearity in the form of a neural network. Then you have another layer. So another layer takes into account interaction between pairs of the input, but these themselves are already consist of interaction between pairs. So you have kind of like a pairs of pairs, and then the next like layer it's pairs of pairs of pairs, and eventually you get an embedding that is much more rich, that takes into account various parts or the combination of various parts in the input. So it's known, you can think about it, the first layer is kind of like pairs of words, takes into account pairs of words. The next layer already kind of whole takes into account maybe whole expressions or different kind of parts of the sentence, etc., etc. So once you go deep in the network, the embedding becomes richer and more meaningful. That is kind of like the whole idea. And then you have a prediction head. So the prediction head is just usually is just a linear layer with if it's a multi-class, which obviously in text it is. So we have a linear and a softmax. So this is a prediction, or the output is a probability vector over the vocabulary. So basically, it gives a vector that assigns a certain probability to each token in the vocabulary. Okay, so this is kind of like a decoder-only transformer for generating text, and the whole idea in during training, we try to minimize a standard loss, which is a cross entropy, and this is the loss between the output, the probability vector, and the actual next word, which is obviously kind of like a one hot vector that assigns a one to the actual word, which is next, and zero otherwise. Okay, so this is kind of like difference or a measure of difference between the actual output and the prediction vector. Okay, so this is kind of like a very simple, I think, kind of basic plain vanilla transformer for generating text. Let's look at an example of a vision transformer. So here the input is a single, or we have an image which is an input, and as we said, the tokens are different parts, kind of different patches of this image. And usually one of the kind of tasks that we use to train the transformer is to mask part of the tokens in the image. Okay, and that we would like to train the transformer to be able to recover the full image um, from the masked image. And this is kind of like one of I would say maybe the main task here. Okay, so we have the original image. We have a masked image, which is just taking kind of masking out different parts, different tokens, or different patches. And we would like the transformer, the network, we train it to kind of recover the full image. Okay, and then we have an encoder vision transformer. So this is the self-attention mechanism applied only to the visible patches. Obviously, if the patches are not visible, meaning we mask them out, we don't take them into account in the attention mechanism. And so the attention mechanism, again, is a repeated application of multi-head attention, say 3, 4 layers of multi-head attention. And eventually, the output of every multi-head attention is an embedding for each token. So at the end of the day, the end of the encoder provides us with M embeddings for the M tokens in the data. So this is the encoder. In this case, this is an autoencoder structure. So now we have a decoder that gets these as input. Okay, so here we would like the decoder to recover the full image. And the input, or now notice that the input is larger than the output of the encoder, because the encoder, the output was only for the visible um, only for the visible patches. But now, instead of the invisible patches, we put kind of placeholders. Okay, so here the length of this list of embeddings is the size or the total number of patches, including those that we masked out. Okay, so those that we masked out are just kind of placeholder, and we try to train the network to be able to, from this part, to recover the full network. This is given an input to another, so this is a decoder kind of part of the attention mechanism. And we have a reconstruction head. So this is another kind of a layer that predicts the pixel or the patches from the different embeddings. Okay, so this is the way we train the transformer to be able to kind of recover a full image from the embedding. Now, there's many things you can do with this kind of transformer. Um, for example, if you would like to use the output of the encoder to be able to perform any learning tasks. For example, want to cluster, want to predict prediction tasks. So you can use, for example, the token embeddings as an input to any learning algorithm that you would like. Okay, so this is, for example, one thing you can do. And one thing I forgot is the loss function. Okay, so basically the loss function here is some measure of difference between the reconstructed image and the original. Finally, let's talk about translation. So this is, here we go back to the original paper of Attention is All You Need. Now the translation application is a bit more complicated than just text. Because here, it's not only you want to predict the next word, but it's not that I have like a single language and I have maybe part of a sentence and I want to predict the next word from a part of the sentence. Basically, what we have two inputs. we want to predict, say we want to predict from English to French. So we have the full sentence in English and we start to translate. So we have on the one hand the full sentence in English, but we also had kind of like part of the sentence we already translated in French. So this is kind of like in French, kind of the idea in the French part of this application, we want to predict the next word, but we also have the full sentence in English. Okay, so this is kind of like a double input. So this is a bit confusing. So if we look at the schematic flow on the left, so we have the upper left is the original sentence in English, I like cats, and we have the encoder block. So this is similar to what we had at the beginning. So encoder blocks, I mean, tokenization, token embedding, position encoding, and all the attention mechanism repeated. And we have the encoder output, which is the embedding of the token. So this is a full attention. Okay, not mask one, because again, the idea when I translate, I have the full sentence in front of me, not only part of the sentence. On the bottom, here we have a masked attention because the bottom, the input is the sentence in French, but only the part I would like to use, only the part I already translated. Okay, so this is kind of a masked self-attention. And the middle is a block that we haven't discussed or haven't presented. It's called cross-attention. And the main idea, it operates similarly to the attention mechanism, but kind of like the impact is between pairs of where one element is from, say, the output of the encoder, the English encoder, and the bottom part is from the mask self-attention. So this is kind of like a cross-attention mechanism, very similar to the original attention, but just operates between between the two. And at the end of the day, we have a linear softmax and the prediction of the next token. So this is kind of like the final part is very similar to the original language or text generating. But what kind of makes this a bit more complicated is the dual input and the cross attention between them. Okay, and this is an image from the original paper. Okay, we have the transformer model architecture. You can see the double input. Here we have an input embeddings on the left, position encoding, multi-head attention, kind of like the standard attention blocks, which we already know, feed forward, and all this repeated n times. And notice that on the right, we have the second input. Here, it's a masked multi-head attention, again, addition and norm, and these two are merged together. The output of the masked multi-head attention, kind of like the target language, and the output of the left, which is a source target. Okay, and these two are also fed into another attention mechanism and a linear and a softmax. So this is kind of like the basic structure of the original transformer meant for translation. Okay, obviously there are numerous architectures by this point for vision, for science, say neuroscience, for biology, for numerous applications, and each one has its own kind of structure and new things. But once you understand, I think the basic building blocks, you'll be able to understand kind of like more complicated and novel structure. That's it.